Hello. Right, same. Hello. Today the webinar is on Taylor series. Okay, so in Taylor and Maclaurin series, and it will be led by David Vaccaro, a guest speaker today. Okay. Oh, waiting for David to join. Welcome, everyone. Hello, everyone. Apologies, slight delay of the start. Hey, David is having technical issues, but we're coming live in a bit. Sorry for the delay. Okay.
Vlad, sorry, technical problem. My Zoom software was not up to date.
Yeah.
So I need the password.
Okay, good.
Oh, but I'm looking forward to this. So Taylor series.
Yep, indeed.
Oh, they've got a treat, absolute treat. Right, am I host? Can I share my screen?
You can share your screen, and you are the host now.
Excellent. And is that working?
Can't see your screen at the moment.
Okay, let's try again. Right, what's sharing now?
Yes, we can see it now.
Excellent. Okay. So you mentioned that last time you'd looked at the Taylor expansion of e to the x.
Yes.
Excellent. Right, let's look at some other really fundamental functions. Let's look at trigonometric functions. And I think I'm going to do something a little bit unusual, which you guys won't have done before. You've probably built up Taylor expansions via differentiation. I'm going to go at it a slightly different way. I'm going to go at it via integration. So here's the question here. So it says points A and B lie on a circle with radius 1. So this is a circular sector with radius 1. And the angle here is theta. And notice theta is written without any units, so I can assume that theta is in radians. And it says that if 0 is less than theta is less than pi over 2, prove that 0 is less than sine theta is less than theta. So how are we going to do that? Well, the question is geometric, so we want to look for some geometry. Now this triangle here, OMB, sorry, OAB, what is its area? Well, its height by simple trigonometry is just MB, so its height is sine theta. So the area is half of the base, which is 1, times the height, which is sine theta. So the area is half sine theta. Or we could have thought about the two sides, 1 and 1, and then the angle between them is theta. So the area is a half of the two sides multiplied by the enclosed angle. So OAB is sine theta. What about the sector OAB? Well, because we're working in radians, the fraction of the circle that we've got is theta over 2 pi. The area of the whole circle would be pi r squared. So in this case, the radius is 1, so it'd be pi 1 squared. So the area of the sector is a half, the pi's cancel, theta. Now, this is where I think we hit a slight philosophical kind of question mark, which is whether you're a physicist or whether you're a mathematician. If you're a physicist, you're probably satisfied with just the claim that it is geometrically obvious that the area of the triangle OAB is less than the area of the sector OAB. So we have half sine theta is less than a half theta. And then also clearly, as theta is bigger than 0, sine theta is bigger than 0. So we have the inequality 0 is less than sine theta is less than a half. If you're a mathematician, you might be a little bit less than satisfied by this claim that it is geometrically obvious that the area of the triangle is less than the area of the sector OAB. So just to sort of get people's brains warmed up, in the chat, try and give the most convincing explanation that you can of why the area of the triangle is less than the area of the sector, or alternatively, what geometric fact you think you would need to prove to establish that the area of the triangle was less than the area of the sector. Okay, nothing has come through from the chat yet. If you're watching the webinar on catch up, you might want to pause and think. So why does this claim hold that the area of the triangle is less than the area of the sector? Well, what you would need to establish is that you would need to establish that the triangle OAB is contained within the sector OAB. So it's a subset. And then there's some axiom of geometry which says that the area of a subset is less than the area of the whole set. And to prove that, you would need to show that this line segment AB lies inside the circle. Okay, that's just as an aside, but that's the geometric fact that this relies on. And you might want to go away and try and prove that this chord AB lies inside the circle. Okay, so I said that I was going to build up Taylor expansions in a slightly unusual way via integration. So if we just look at this inequality for a moment, as long as we're less than pi over 2, if I was to draw my graph of y equals sine theta, and I was to draw the line y equals theta, the curve y equals sine theta always lies beneath the line. And in fact, we can see that this actually holds for theta greater than 0, because the line is already at pi over 2 when x is pi over 2, and then will continue to rise, and that's already bigger than 1. So this inequality 0 is less than sine theta is less than theta holds for all positive theta. Can I integrate this inequality? Well, yes, because this orange area, this area under the curve y equals sine theta, actually, I'm not going to integrate all the way up to pi over 2. I'm just going to integrate up to some positive value theta. So I'm just going to look at this area here, that if I integrate from 0 to theta of sine, I'll use a different variable t, dt, then that is less, this orange area is contained within this green area. So this integral is less than the integral from 0 to theta of t dt. Okay, well, let's see what happens when we integrate. So what function differentiates to sine t? That's cos t. What function integrates to t? That's a half t squared. And I realize at this point that I've used a little bit of a steam hammer to crack a nut, because the green area is just a triangle. So I could have just used the fact that the base is theta and the height is theta. And so the area is a half theta squared. And so now I substitute in my limit. So I get cos theta, differentiates to sine t is minus cos t. So I get minus cos theta minus minus 1 is cos theta. So 1 minus cos theta is less than a half theta squared, which if I rearrange it gives me cos theta is less than 1 minus a half, sorry. I get that 1 minus a half theta squared is less than cos theta. I also know that cos theta is always going to be less than or equal to 1 with inequality strict if theta is bigger than 0. So I won't insist that theta is bigger than 0, so I can just put less than or equal sign. So what have I done? I've integrated this inequality, which was an inequality involving sine, and I've now got an inequality involving cosine theta. So graphically, what this means is that my cos graph for positive theta lies beneath the line y equals 1, but above this function 1 minus a half theta squared, which is a parabola. And I'm just going to see if anyone is alive on the chat. But what do you think is going to happen next? So I've started with an inequality for sine theta. I've integrated, and it's given me an inequality for cos theta. Well, let's see what happens if I integrate again. So if I integrate the lower curve between 0 and theta, and again, I'll introduce a new variable t, that's less than the integral of cosine between 0 and theta, which is less than the integral of 1 between 0 and theta. And let's have a look at the different integrals. So this integral is just the integral of a quadratic. So it's t minus 1/6 t cubed, evaluated between 0 and theta. The integral of cos t is sine t, because the derivative of sine t is cos t. And the integral of 1 is just theta. So I should have put a different variable, so I'll put t, evaluated between 0 and theta. And now when I substitute in my limits, I get theta minus 1/6 t cubed, theta minus 1/6 theta cubed is less than or equal to sine theta is less than or equal to theta. And we notice that something quite funky has happened, is that the upper bound for sine theta hasn't changed, but the lower bound for sine theta is no longer 0, but is this new expression, which is some cubic function. So what we've established is that my sine graph, so y equals sine theta, lies beneath its tangent, which is y equals theta, but lies above this cubic function. So what we've done is we've sharpened up the lower bound. So this is a sharper lower bound. What we can also see is that if we were to approximate sine theta by theta, then the error is at most 1/6 theta cubed. So we know for small theta, that error term will decay. Now, I imagine everyone at this point will realize what I will do next. Okay, so what do you think? I've now got an inequality for sine theta, How can I get a new inequality? Well, I can simply integrate again. So I can integrate from 0 to theta of t minus 1/6 t cubed is less than the integral from 0 to theta of sine t is less than the integral from 0 to theta of t, just integrating that inequality. And now I get 1/2 t squared minus 1/24, which I can write as 1/4 factorial t4, 0 theta, is less than or equal to negative cos t, 0 theta, is less than or equal to 1/2 t squared, 0 theta. So I get 1/2 theta squared minus 1/4 factorial theta 4 is less than or equal to minus cos theta plus 1, and that's less than 1/2 theta squared. And if I rearrange the inequalities, I get the same lower bound for cos theta, which was my quadratic function. But I get a better upper bound for cos theta. So previously my upper bound was just 1. But I now get that the upper bound is this quartic term. Okay. As an exercise, okay, and this would be a natural sort of proof by induction, you can continue this process and you can continue sandwiching cos theta and sine theta between two polynomials. Okay. So what this shows is this actually, in some sense, gives us a little bit more kind of precision than what you would normally see in sort of Taylor expansion. So you'd often see something like this as a small angle approximation for cos theta. Cos theta is approximately 1 minus 1/2 theta squared. But this expression is much better than just a simple approximation, because it actually gives you what are called lower bounds and upper bounds. So what we can see is that this classic small angle approximation for cos theta is, on the one hand, always an underestimate. But on the other hand, what we can see is that the error is at most minus 1/4 theta to the power 4. So when theta is small, the error is, we've now got a bound on how big the error is. If you were to continue this estimation process, then our estimate for sine theta would be theta, then minus theta cubed over 3 factorial, then plus theta 5 over 5 factorial, then minus theta 7 over 7 factorial, and so on. And our estimate for cos theta is 1 minus theta squared over 2 factorial, plus theta to 4 over 4 factorial, minus theta 6 over 6 factorial. Now, you could have got the same Taylor expansions by repeated differentiation, but this integration idea actually gives us a little bit more, gives us an extra fact, which is that the approximations are alternately overestimates and then underestimates. Okay, so we've done this question here, where we've established these Taylor expansions for cos x and for cos x and sin x. Also on this question, it says, what happens when you differentiate these expressions? Well, we shouldn't be surprised in many ways. So let's see what happens when we differentiate cos x. Well, the 1 differentiates to 0. The x squared over 2 factorial term differentiates to negative x. x4 over 4 factorial, we pull the 4 down, so we lose a 4 from the 4 factorial, so we get x cubed over 3 factorial. Then when we differentiate the minus x6 to the 6, we get minus x5 to the over 5 factorial. And this is just exactly the same as the Taylor expansion for sine, but with a negative. And if we differentiate the expression for sine x, we just get 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial. And that just gives me the Taylor expansion for cos x, which is exactly what I would have hoped for. Okay, so this question was a little bit of a novelty. So this is Taylor expansions from integration. Okay, people are a little bit quiet. I'm just going to double check that people are still watching and people are still happy. If you're happy with that question and ready to move on, put a thumbs up or just put a happy smiley face into the chat. If not, please put any questions into the chat and I'll address them there. We've got some happy faces. We've got some thumbs up. Cool. People really are there. Okay. Do feel free to contribute into the chat. There's nothing worse than doing these online sessions sometimes when you just feel you're like a crazy person speaking out into the, into the ether. It's really reassuring to know that people are indeed there. Right. The next question we're going to look at is we're going to look now at new Taylor expansions from old. We're going to look at new Taylor expansions from old ones. So if you've got one Taylor expansion, how can you manipulate it to get new Taylor expansions? So let's. Oh, this one's very nice actually towards the end. So I'm just going to snip this. Okay, so we're going to look at a expansion which is familiar. What name would people give, put it into the chat, to this expansion here? 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x4 plus x5 plus dot, dot, dot. You can think of this as a Taylor expansion, but where else have you met this series? All people are quiet in the chat. What sort of series are good? Geometric series, geometric sequence, because 1 plus x squared is just a geometric expansion with common ratio x. Right, let's look at what it says. It says by squaring both sides. Okay, now here I'm going to sort of lose my mathematician's instinct and I'm just going to be rather fearless and not worry too much about whether it's sort of justified to multiply sort of infinite series and open infinite brackets the way we would normal brackets. So it asks me to square the series. So I'm going to try and square 1 plus x squared plus x cubed plus dot, dot, dot forever. So let's try and square it. Okay. I don't know how people open brackets, but I'm just going to open the bracket quite systematically. So I can put the 1 and the 1, so that gives me a 1. How can I make a term? And if you're watching this on the webinar, I'd really recommend sort of pausing at this point and trying to do the series expansion yourself. how can I make a term involving x? Well, I could put the x with the 1, or I could put the 1 with the x. So that would give me plus 2x. To get an x squared term, I could put the x squared with the 1, the x with the x, or the 1 with the x squared. So that gives me 3x squared. And we can now see the pattern, and we can assume that we will get 4x cubed and so on. Okay, why? Because to make x to the n, we've got a 1 from the first bracket and an xn in the second bracket, an x in the first bracket and an x to the n minus 1 in the second bracket, all the way up to x to the n in the first bracket and 1 in the second bracket, which is m plus 1 terms. Okay, so if I square 1 over 1 minus x, I should get this series. I should get this series expansion. Now, there's a job of work to show that you can square infinite brackets in that way, but if we're fearless, then we can. Okay, next sort of way of getting new Taylor expansions from old. Instead of squaring them, what else could I do to both sides? So something else I could do to both sides would be to differentiate both sides. So what happens if I differentiate 1 over 1 minus x? Well, that's the same as differentiating 1 minus x to the power of minus 1. So by the chain rule, I get a minus 1 times 1 minus x to the power of minus 2. And I differentiate inside the brackets, and I get another minus. So overall, if I differentiate, I get 1 over 1 minus x all squared. What happens if I differentiate the original series, though? So what happens if I differentiate 1 plus x squared and so forth? Well, the 1 differentiates to 0, the x differentiates to 1, the x squared differentiates to 2x, the x cubed differentiates to 3x squared, the x to the 4 differentiates to 4x cubed, and I get the same series expansion that I got above when I squared the brackets. The first year at university, if you do a maths degree, quite a lot of time is spent showing that inside the radius of convergence, so where in the section of the plane where the power series converges, power series tend to be quite stable under term-by-term differentiation, term-by-term integration, and multiplying power series together. Okay, but for the moment, you'll just need to take those results on trust. Okay, before we go on with the printed questions, so the next printed question will be what happens when we integrate both sides. I'm going to do an interesting bit of maths, which I hope to return to, where I'm going to prove a very familiar result in a very high-tech way. So I'm going to start with this expansion. 1 over 1 minus x all squared. And what I'm going to try and do, or what I'm going to challenge you to do, is find the expansion of 1 over 1 minus x all cubed. Okay, and we're going to do this in 2 ways. And just to check if people are alive, put in the chat 2 ways that you think you could find the expansion of 1 over 1 minus x all cubed. So someone's put binomial expansion, so the kind of infinite binomial expansion. I'm going to ban that a little bit. Regard what we're going to do as a proof of the binomial expansion. Excellent. So we could cube the expansion in part A. Well done. And we've already squared it, so we haven't got that much more to do. Or what else could we do? How else could we go from 1 over 1 minus x squared to 1 over 1 minus x cubed? Okay, we could do the Taylor expansion. But how did we go from 1 over 1 minus x to the minus 1 to 1 over 1 minus x to the minus 2? We differentiated term by term. Okay, so I'm going to do both of these ways. So let's look at 1 over 1 minus x cubed. And let's do it by multiplying Taylor expansions together. So we've got 1 over 1 minus x times 1 over 1 minus x squared, which as Taylor expansions is 1 plus x squared plus x cubed plus dot, 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 multiplied by 1 plus 2x plus 3x squared plus 4x cubed, and so forth. And what I'm going to do now is I'm going to be bold, and I'm going to open these infinite brackets. And I opened it last time just by kind of sort of FOIL, essentially. For people who prefer a sort of grid method, I'm going to do it by a grid method now. So this is my 1 plus 2x plus 3x squared. This is my 1 plus x squared plus x cubed plus x4. And let's start multiplying out. So we've got 1, then we've got 2x, 3x squared, 4x cubed. Then we've got x, 2x squared, 3x cubed, 4x to the 4. Then we've got x squared, 2x cubed, 3x to the 4. Then we've got x cubed, 2x to the 4. Then we've got x to the 4. And then if we simplify terms, or sorry, if we gather terms of the same type, we've got a units term, which is 1. We've then got 2 terms involving x. We've got 1x and 2x. And then we've got 3 terms involving x squared. So we've got 1 plus 2 plus 3 x squared. And then we've got 1 plus 2 plus 3 plus 4 x cubed, which simplifies to 1 plus 3x plus 6x squared plus 10x cubed. Okay, let's see if we get the same result by differentiating my expression for 1 over 1 minus x squared. So let's differentiate 1 over 1 minus x all squared. So let's differentiate 1 plus 2x plus 3x squared plus 4x cubed, and so on. And we go up to n plus 1 x to the n. I'm going to look at the general term. So if we differentiate on the left, we get, by the chain rule, 2 over 1 minus x cubed. And if we differentiate on the right, we get 2 plus 6x plus 12x squared. And then we get n plus 1 times n xn minus 1. And then if we divide by 2, we get 1 over 1 minus x cubed is equal to 1 plus 3x plus 6x squared plus dot, dot, dot. My x to the n minus 1 term is n plus 1 n over 2 x to the n minus 1. Now, on one level, all I've done is I've shown that I've got the same series expansion for 1 over 1 minus x cubed in two different ways. And for those of you who've done the infinite binomial expansion, it's the same as the infinite binomial expansion. But I want you all now to stare at these two expressions and tell me what familiar bit of maths have we just proved in a completely unfamiliar way. So I've got two Taylor expansions for 1 over 1 minus x cubed. Okay, one which I obtained from cubing my original Taylor expansion. So that was this line of working here. And one which I obtained from repeated differentiation. If I can assume that they give me the same Taylor expansion, what result have I just proved? Okay, simpler question. What are these numbers? Where have we seen these numbers before? 1, 3, 6, 10. Yeah, they're the triangle numbers. Okay, let's look back at our working and see why we got the triangle numbers. Well, my coefficient of x cubed, for example, was 1 plus 2 plus 3 plus 4. So this was just the fourth triangle number. So my series expansion, my general term for xn is the n plus 1th triangle number. So my coefficient of x to the n minus 1 is the nth triangle number. So what does that tell me about this term here? Well, this is the coefficient of x n minus 1. So what I've just proved that the nth triangle number is n times n plus 1 over 2. Okay. If you like that fact, if you like that argument, and if you understood it, put your emoji into the chat. I personally love it, so I'm going to put a smiley emoji. If you didn't understand anything there, then please put any questions into the chat. Good, I've got some thumbs up. Okay, and what you've just seen there, okay, and I imagine it's the first time that many of you will have seen it, is you have, oh, I don't recognize that. What's that emoji? There's a tortoise. Have I taught you something? Or are you feeling sick? I don't know. But what I imagine is new for you is that argument, okay, where I've proved something about a sequence using a Taylor expansion. And that is your first example of something which turns out to be a really powerful idea in pure mathematics, which is a generating function. Okay, and if there's time at the end, I will do another example of generating functions. Are people happy for me to continue? I assume so. Yep. So let's go back to new Taylor expansions from old ones. So what expansion do you get when you integrate both sides? So we're going to start with our geometric series. 1 over 1 minus x is 1 plus x squared plus x cubed plus dot, 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 dot. And we're now going to integrate this between 0 and x. And I better introduce another variable, 1 minus t dt. And that's the integral from 0 to x of 1 plus t squared plus t cubed plus dot, dot, dot dt. Right, I'll do the right-hand integral first. So that's nice and easy because this is just a polynomial. So I get t plus t squared over 2 plus t cubed over 3 plus t4 over 4 plus dot, dot, dot. Evaluated between 0 and x. So I get x plus x squared over 2 plus x cubed over 3 plus x4 over 4 plus dot, dot, dot. What about the integral on the left-hand side? Any suggestions in the chat? Well, the derivative of the bottom is -1. So if I just modify the function slightly, I've got function on the bottom, derivative on the top. So it's the integral is the natural log of the denominator. Evaluated between 0 and x. So I get negative ln 1 minus x plus ln 1, which is 0, is x plus x squared over 2 plus x cubed over 3 plus x4 over 4 plus dot, dot, dot. And if I now rearrange, I get log of 1 minus x is minus x squared over 2 plus x cubed over 3 plus x4 over 4 x dot, dot, dot. Okay, so this should be the Taylor expansion of ln 1 minus x. Okay, now you could get this Taylor expansion by term differentiation of 1 minus x and evaluating it at 0, but you can also obtain it from modifying this known Taylor expansion of the geometric series. And then let's look at the next question. So find the value of the following series: 1 minus a half plus a third minus a quarter plus a fifth. So this is one of these easy if you spot it. What value of x would I need to put in to get this infinite series? Excellent. X equals -1. Someone's put that into the chat. So if I put x equals -1, I get that the natural logarithm of 2 is 1 minus a half plus a third minus a quarter plus a fifth. Okay, we're now going to do a survey. We're now going to do a poll. So question number 1 is, do you think this result is true? And then question number 2, do you think the above proof is valid? There's no reason why you would know the answer, so you're just in some sense just going to have a little bit of a guess. Well, the validity one, I think, is more, there's more clear cut that there is a right answer. Is anyone feeling brave? Do you think that log 2 really is 1 minus a half plus a third minus a quarter? Okay, what turns out to be the case is this is indeed true. But the above argument is not really valid unless we're a little bit more careful. What is the issue around substituting in x equals -1? Well, if we think back to our original geometric sequence, that geometric sequence is only valid for values of x that lie strictly between -1 and 1. Otherwise, this series doesn't converge. So it isn't really justifiable to use the value of x equals -1 in that expression. But in this instance, it does turn out to give the right answer. What's the moral there is that with Taylor expansions, with these infinite series, and this is actually true sort of historically, you often get the right results if you just sort of are a little bit fearless and sort of assume that things work. But actually in the background, there's more kind of delicate analysis that needs to be done. And that's something which one would do in university. Okay, but this does turn out to be a true fact. Okay, any questions about that section of starting with a Taylor series and then modifying it to get new Taylor series? Very good question in the chat. How would you prove it properly? Very, very, very good question. The correct answer is to do something like what we did in the first question with the sine and the cosines, and to get upper and lower bounds, and to show that you get an, and to actually control the error term, and to show that the error term goes to 0. I won't try and reconstruct this here, but that's the answer of the question. How you prove things rigorously is virtually always finding upper and lower bounds and then showing that they squeeze together to the same thing. Excellent question though, Ben. Okay, any other questions, or are we happy to move? Are we happy to move on? Happy to move on? All good. Okay, people in the webinar. Okay, your reward for being present here in the webinar is you're going to be able to choose between two amazing pieces of mathematics. Okay, so we'll just do this on a simple vote. And if there's time, we'll do both, but if not, we'll only do one or the other. So option number 1 is, would you like to see how the function e to the x is related to cos x and sin x using Taylor series? Or option number 2, would you like to use Taylor series to get an expression for the Fibonacci sequence? Twos are in the lead. Right, 2s of 1. Okay. So this is the Fibonacci sequence via Taylor series. Okay, and the approach we're going to use is we're going to use the approach of generating functions. Okay, so I'm going to start by writing the Fibonacci sequence. I'm going to write 1, 1, 2, 3, 5, 8, 13, and so on. And for the purposes of this, I'm going to call 1 the 0th Fibonacci number, this 1 the first Fibonacci number, this 2 the second Fibonacci number, and this 3 the third Fibonacci number, and so on. I don't know if that's standard. If my formula is going to either be the normal Fibonacci sequence or 1 out. And what I'm going to do is I'm going to have this amazing idea. So a Taylor expand, on the one hand, we know that if there is a function, f of x, then there is a Taylor-Maclaurin expansion defined by the sequence of coefficients. Okay, so if I've got a function, I'll just say smooth. The Taylor-Maclaurin expansion maps that to a sequence, okay, i.e. the sequence of its coefficients. But alternatively, if I've got a sequence, like here I've got the Fibonacci sequence, I could say I'm going to define a smooth function, and this is called the generating function. So what I'm going to do is I'm going to define a function, and I'll just call it f of x. And the coefficients of powers of x are going to be my Fibonacci sequence. So f of x is going to be 1 plus x plus 2x squared plus 3x cubed plus 5x4 plus 8x5 plus 13x6 plus ... fn xn. Okay, so what I'm going to try and do, okay, and if you're watching this on catch up, I'd recommend sort of pausing at this point, is how can I find the function f? Well, let's think about what I know. I know that the Fibonacci sequence can be generated by adding successive terms. So if I multiply my function f of x by x, everything just shifts along one. So I get x plus x squared plus 2x cubed plus 3x4 plus 5x5 plus 8x6 and so on, plus f of n minus 1 xn. But now what I notice is that if I were to add these two functions together, in the units coefficient, I just get 1. In the x coefficient, I get x plus x, which is 2x. I then get 3x squared plus 5x cubed plus 8x4. What do people notice about these numbers? 1, 2, 3, 5, 8. Well, what I can see is that they are Fibonacci numbers. Okay, but everything is just a little bit wrong. Okay, is that the 5, instead of being with the x cubed, sorry, the 5, instead of being with the x to the power 4, is with the x cubed. So I've got f of x plus x fx is this thing. And again, this would be a good place to sort of pause. But I'd invite everyone in this sort of webinar here to think about how I can now use this observation to relate f of x plus x fx back to my original function. Well, with a little bit of thought, you could realize that what I really want to do is I want to move this 5 back into the x4 position. So what I'm going to do is I'm going to multiply by x. And everything shifts along. So I get x plus 2x squared plus 3x cubed plus 5 x4. And then we get fn xn. And so what we can see here is now every term is the same as the term in the original expansion for fx. The only thing which is changed is that we don't have a 1 anymore. The 1 is missing. So this right-hand side here is f of x minus 1. Okay, so now with a little bit of rearranging, I get f of x is 1. Sorry, f of 1 is f of x minus x fx minus x squared fx. That's equal to 1. And so fx is 1 over 1 minus x all over x squared. Okay, does anyone have any questions at this point? If you're happy, because I'm aware I did that a little bit quickly, if you're happy, put a thumbs up. Thumbs into the chat. Right, there's also a very good question, which is what does the x represent? And to be honest, the variable x in this instance doesn't Sorry, I think I got kicked out of the meeting. Can people see me again? Can people see and hear me? Yes, good. So this x doesn't really represent anything, but we're just exploiting the fact that a Taylor expansion involves infinite number of different powers of x, and that allows us to represent a sequence. Right, what I'm going to do actually is, it's quite useful that it's kicked me off my OneNote, because I'm just going to go to Wolfram Alpha. I'm just going to show you that we've indeed, the Wolfram Alpha output is just going to show us exactly what's going on in some sense. So I'm just going to share a window. Here we go. So here is my function 1 over 1 minus x squared. Okay. And here it is. Okay. It's just a reciprocal quadratic. Okay. It's got some sort of shape. But what we can see here, okay, is that if we look at its Taylor expansion, I didn't want that. So if we look at the Taylor expansion of this function is 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4. Okay, and we suddenly recognize these numbers as 1, 1, 2, 3, 5. Okay, and if it gave me more terms, the next term would be 8x5. So what this means, okay, it's a little bit like, I think there's a spy novel. I think there's something called the Da Vinci Code, which is sort of based around the Fibonacci numbers in some way. I've not actually read the book, but what you could picture is this. Imagine I was a spy, okay, and I wanted to send you the Fibonacci sequence. Yeah, and I wanted to send you all of the Fibonacci sequence. I could send you this function 1 over 1 minus x squared. And anyone looking at it would be like, I don't understand this message. But because you knew to calculate the Taylor expansion, if you calculated the Taylor expansion, you would find this whole Fibonacci sequence. So this Fibonacci sequence is contained within the information of the Fibonacci sequence is contained within this function. So what that means is that if we could find the Taylor expansion of 1 over 1 minus x squared in a second way, so if there was a second way of finding this Taylor expansion, we would have a formula for the Fibonacci numbers. So earlier on, we did a much simpler example. We showed that if we cubed 1 over 1 minus x, we got a sequence that encoded the triangle numbers. So this this function 1 over 1 minus x cubed is the generating function of the triangular numbers. We did find that Taylor expansion in a second way, and that gave me a formula for the triangular numbers. Okay, what we now need to do is something similar for the for this function 1 over 1 minus x squared. Okay. Okay, any suggestions of a useful or sensible thing? Oh, there's questions in the chat. Oh no, I've dealt with those questions. Okay, so any useful suggestion of what might be a useful thing to do to this denominator? So we've got x squared minus x minus 1. What could we do to that denominator? Well, it's a quadratic. Okay. So a quadratic can be factorized. Okay. And it factorizes into its roots. So we'll call the roots alpha and beta. Okay, so let's solve this quadratic. So we've got x squared minus x minus 1 equals 0. So we've got x equals 1 plus or minus the square root of 1 plus 4 over 2. So we've got 1 plus root 5 over 2, or x equals 1 minus root 5 over 2. And we'll give these numbers their traditional name. We'll call 1 plus root 5 over 2 phi, and we'll call 1 minus root 5 over 2 phi hat. Okay, so we can write this as x minus phi, and then x minus phi hat. Just a little bit of simplification. Phi times phi hat is equal to -1. If you don't believe me, just multiply them together and check. So if I multiply, I'm going to multiply both sides of the expression here by -1, but I'm going to do that by multiplying by phi hat. So I get 1 minus x squared is phi hat x minus phi hat, multiplying this bracket by phi hat, times phi x minus phi hat. But then phi hat is -1, so I can write this as 1 plus phi hat x times 1 plus phi x. Okay, so my generating function for fx Okay. Any suggestions about what to do now? To rearrange this to get a nicer expression for this function?
Sir,
Yeah.
I don't think you're sharing your screen right now.
Oh my word. That must have been a real nightmare. Oh my word. Thanks for letting me know. Well, at what point was I last sharing it?
I think you said that you were going to reshare after you left, but I don't think it ever happened.
Oh my God.
About 10 minutes ago.
Oh my word. So, okay, so I'd got to, okay, so had I got to this, I'd got to this point where I'd established, the generating function for the Fibonacci numbers. Okay,
Yeah.
so this function here, 1 over 1 minus x squared, this encodes the Fibonacci numbers. Okay, so I haven't done too much since then. Okay, what I've done is I've just factorized this quadratic by finding the roots of, sorry, this should be x squared plus x plus 1. By finding the roots of this, quadratic equation. Okay, and what I've done is I've reached this point. Yeah. Oh my word. Okay. Okay, so what I've done is I've factorized the quadratic at the bottom. Okay, and I've rewritten it in terms of its roots, phi and phi hat. Okay, so I think you just need to take on trust. Okay, that 1 minus x squared is 1 minus phi x times 1 minus phi hat x, where phi and phi hat are the roots. So, and specifically, phi is 1 plus root 5 over 2, and phi hat is 1 minus root 5 over 2. So my question is, what can we do now, okay, to rewrite this expression in a format where we can more easily find the Taylor expansion? So phi and phi hat are just constants, they're just numbers. So what sort of expression do you think I could write that would be equal to this fraction? So in other words, how do you think I could make a fraction with a denominator which was the product of these two things? Well, if you think about the way that you add fractions, okay, the way that you add fractions is to make a common denominator. So what we could add is we could add fractions, one with denominator given by 1 over 1 minus phi hat x, and one with denominator 1 minus phi x. And if we were to choose A and B correctly, we should be able to get a numerator that was equal to 1. Okay, so again, if you're watching this on catch up, this would be a very good place to pause it to try and find the A and B. Those of you in the know will know that this method is a method called partial fractions. Okay, so let's make a common denominator. So we get 1 minus phi hat x, 1 minus phi x. And then we get A plus B minus phi plus phi hat. Sorry. So our numerator is A plus B. My pen has stopped writing. Everything is against me at the moment. Okay, so we've got A plus B. This is a plus. I've just got a sign wrong somewhere. And then we've got plus phi hat. No, we've got A phi. So we've got minus A phi plus B phi hat x is equal to 1 over 1 minus phi hat x. 1 minus phi x. 1 minus phi hat x. 1 minus phi x. Okay, so to equate coefficients, we get that A plus B is equal to 1. And then we get A phi plus B phi hat equal to 0, because we want the 1, but we don't want any x coefficients. So let's find the values of A and B. So we've just got two simultaneous equations to solve. So we've got A phi plus B phi is equal to 1. So if I subtract, I get B phi hat minus phi is equal to minus 1. And if I do a similar cancellation, I get a phi minus phi hat is equal to -1 as well. But if I look at my expressions for phi and phi hat, phi minus phi hat is just the difference between them. The ones cancel, and then I get left with a √5 term. So I get B is -1 over, so I get B 1 over √5, and I get A is -1 over √5. Okay, so to recap, I showed in the first part that the Fibonacci sequence was 1 minus x squared. I then have, by factorizing this quadratic and then splitting it into two partial fractions, I can rewrite it as this. Okay, so this is just a little bit of algebra, okay, to play around with this function to split it. So I've split it into two parts. So I've split the fraction with the quadratic numerator into two parts. And so this method here, which some of you will have met already, this is called partial fractions. Okay, all you've got to trust me of is that this gives an alternative way of writing this generating function. Now, at first glance, it looks like I've made everything more complicated. But why can I write down the Taylor expansions of these two parts? So what is the Taylor expansion of 1 over 1 minus phi x? Where earlier on in this webinar have we seen something that a fraction that looks like this? Let's write it in a way which is maybe slightly more familiar. What can you tell me that 1 over 1 minus r is equal to? Well, we recognize 1 over 1 minus r as the sum of a infinite geometric progression. So this 1 over 1 minus phi x, we can write as 1 plus phi x plus phi squared x plus phi cubed x, and so on forever. Okay, similarly, the 1 over 1 minus phi hat x, we can write as an infinite geometric series. And then we can then subtract and combine them, and we get that fx is equal to 1 over √5, and then we get phi minus phi hat x plus phi squared minus phi hat squared x squared plus phi cubed minus phi cubed x cubed. Okay. But what do we now think that these terms are going to, what do we now think that these terms are going to give me? What we decided earlier was the coefficients of the powers of x in the function fx. Well, we decided earlier this should give me the Fibonacci, this should just give me the Fibonacci, this should just give me the Fibonacci sequence. Okay, so the values of phi is roughly 1.618, phi hat is negative 0.68. So for large n, the phi hat term goes away. So what we get for large n, the n Fibonacci number is something like phi to the power n over root 5. So what I'm going to do is I'm just going to stop sharing briefly and share a Wolfram Alpha with you. Okay, so let's take the golden ratio, okay, which is 1 plus square root 5 all over 2. And let's, I don't know, raise that to the power 10 and divide it by square root 5. And what we see is that the value is 55.00, which is very close to 55. Okay, the difference is the contribution from that phi hat term. Okay, so if I was to include in my numerator, oh no, wait a minute. Getting the brackets in the wrong place. So phi minus phi hat, there we go. We get exactly 55. Okay, so what we can see here is that the 10th Fibonacci number is the root of that quadratic to the power 10 minus the other root of the quadratic to the power 10. And if I change the power here, I get the next Fibonacci number. So just to recap what happened there. Let's run this through from the beginning. So I started with the Fibonacci sequence. I then decided that if I had a sequence, I could do the opposite of a Taylor-Maclaurin expansion and use the sequence to give me a function. So I defined this mystery function whose Taylor expansion was the Fibonacci numbers. I then did a little bit of algebra to utilize the Fibonacci relationship to find out what this mystery function was. So this mystery function was 1 over 1 minus x squared. I then factorized the quadratic and used a little bit of partial fractions to write that rather than the reciprocal of a quadratic, but to write it as the sum of the reciprocal of two linear brackets using a method that you will meet called partial fractions. So that gave my Fibonacci sequence in partial fraction form as the reciprocal of these linear expressions. But then the reciprocal of these linear expressions, I can find the Taylor expansion. And in fact, I recognize the Taylor expansion as the sum of a geometric sequence. So that then means that I could have got the Taylor expansion of fx in a different way using an expression that involved the power of these roots, and in particular, the important root, so the one which doesn't decay as n increases, is the golden ratio, and that allows me to find the nth Fibonacci number. Okay, so some quite a few technical details, okay, but I hope that you can go away and you can look through those technical details yourself, okay. But what this gives is a Taylor series method of finding the Fibonacci sequence. Okay, despite losing my screen for a little bit, I hope that people enjoyed that. Okay, any questions before we finish? Notwithstanding missing the screen, did people like that last proof? Definitely good. Okay. There's a whole rich There's a whole rich theory of generating functions and ways of defining generating functions in this way. Super. I think we should call that. I think we should probably call that a night. Does anyone have any final questions before we finish? Super. Well, I'm going to do the remote learning wave. I'll say goodbye to everybody, and I'll see you again soon for the next webinar. Thank you, everybody.